Basic Mechanical Drives, Part 3, based on a SlideShare presentation by James Shearer, adapted, added to and presented by me, John LeGuy. Here's legal stuff. So, the overall purpose of this is to look at mechanical drives. We're now going to look at belt drives. Belts are utilized to transfer energy from a driver to the driven, and usually transfer one speed ratio to another through the use of different sheave sizes. V-belts are constructed from three basic components, which vary from maker to maker. A load-carrying section to transfer the power, rubber compression section to expand sideways in the groove, and a cotton or synthetic fiber cover to resist abrasion. The standard V-belt must ride in the sheave properly. If the belt is worn, or the sheave is worn, then you will have slippage of the belt and transfer and power and speed will change. If a V-belt drive is located near oil, grease or chemicals, the V-belt could lose their capacity through the deterioration of the belt material, quickly resulting in belt breakage or massive slippage. Belt drives are used to transmit power between a drive unit and the driven unit. For example, if we have an electric motor and a contact roll on a conveyor, we need a way to transmit the power from the electric motor to the roll. This can be done easily and efficiently with a belt drive unit. Belt drives can consist of one or multiple belts, depending on the load that the unit must transfer. The belts need to be matched with the sheave type, and they must be tight enough to prevent slippage. Examples of the different belt and sheave sizes are as follows. Fractional power V-belts, sizes 2L, 3L, 4L and 5L. Conventional V-belts A, B, AB, C, D and E. Conventional cogged V-belts AX, BX and CX. Narrow V-belts 3V, 5V and 8V. Narrow cogged V-belts 3VX, 5VX. Power band belts. These use the same top width designation as the above belts, but the number of ribs, or hands, is designated by the number preceding the top width designation. For example, a 3-ribbed 5V belt will be labelled 3/5V. Positive drive belts XL, L, H, XH and XXH. V-belts are best suited for transmitting light loads between short-range sheaves. They are excellent at absorbing shock. When an overload occurs, they will act as an overload device and slip, thereby protecting valuable equipment. They are much quieter than the other power transmission devices such as chains. Because of their design, they are easier to install and maintain than other belt types. Other than the occasional retensioning, V-belts are virtually maintenance-free. When properly installed and maintained, V-belts will provide years of trouble-free operation. Cogged belts provide even longer life than conventional V-belts because of their design. They run cooler than conventional belts, thereby increasing overall life of the belt. Joined or power band belts provide a good alternative to pulsating drives where standard V-belts have a tendency to turn over. They function like a standard V-belt, with the exception that they are joined by the top fabric of the belt. These belts can be used with the standard V-belt sheaves, making selection and installation easy. Positive drive belts, sometimes called timing belts because they are often used in application where timing a piece of equipment is critical. However, they are also used in applications where heavy loads cause standard V-belts to slip. They are flexible and provide the same benefits as standard V-belts, but their alignment is more critical. Sheaves are made of cast steel for heavy-duty applications. For lighter applications, they are forged out of steel plate. Cast iron sheaves are always used in applications where fluctuating loads are present. They provide a flywheel effect that minimizes the effect of fluctuating loads. When they are mounted to a shaft, sheaves should be straight and have little or no wobble. For drives where the belt enters the sheaves at an angle, deep groove sheaves are available. These are especially useful when the belts must turn or twist. Deep groove sheaves can be used anywhere belt stability is a problem. In some cases, one drive shaft drives more than one driven shaft. When this occurs, more than one sheave can be mounted on one shaft. This is necessarily only when sheaves of more than one size are needed. If the drive sheaves are the same size, one multi-belt sheave can be used. Most sheaves are balanced and capable of belt speeds of 110 km per hour, or roughly 2,000 meters per minute. If you note excessive vibration during operation or excessive bearing wear, you may need to balance or replace the sheaves. The size of the sheaves in a belt drive system determine the speed relationship between the drive and the driven sheaves. For example, if the drive sheaves have the same size sheave as the driven, then the speed will be equal. If we change the size of the driven sheave, then the speed of the shaft will also change. We know that the speed of an electric motor and the size of the sheaves, and now we can calculate the speed of the driven shaft by using the formula. I'll give you a few moments to have a look at this, and the answer is 900 RPM. Often, when a mechanic has to change out belts, the number of the belt can't be read, or the belt is broken or missing. So what should you do? Take a tape measure, wrap it around the sheaves to get the belt length. There's not a very accurate way to determine the length. So usually the mechanic ends up taking a number of different size belts, hoping to have the size that will fit. There's another way. You take a couple of measurements, then use a simple formula to calculate the actual length that is needed. First, move the sheaves together until they are close, as the adjustment will allow. Then move the motor or drive out of its travel. Now you're ready to take the measurements. The following information is needed to find the belt length: the diameter of the drive sheave, the diameter of the driven sheave, and the center-to-center distance between the shafts. Using the equation given, I'll give you a few moments to try that, and the answer is 2489 millimeters, or 98.26 inches. In order to calculate the speed of a belt in meters per minute, the following information is needed: the diameter of the sheave that the belt is riding on, and the shaft RPM of the sheave. With this information, we can use the formula, and we find that the answer is 848 meters per minute. V-belt maintenance. Routine maintenance is essential if a belt drive is to operate properly. Belt maintenance should include regular checks of belt alignment and tension. You should also perform frequent inspections of the sheaves and shafts. Routine maintenance will extend the life of the sheaves and belts. Belt drive maintenance requires little time, but it must be done regularly. Keeping the belts clean and free of oil and grease will help ensure longer belt life. Never force a V-belt onto a sheave. There have been a number of injuries to fingers and hands as a result of this. It can also break the inner strings of the belt, leading to premature failure. The belt should never ride in the bottom of the sheave. The sheave is deeper than the belt. The belt is made to ride near the top of the sheave. The belt may wear to the point that it is riding on the bottom of the sheave. If so, it will slip no matter how much tension is applied to the belt. Keep used belt sets together for use on multi-belt drives. Routine Routine preventive maintenance is essential if a belt drive is to operate properly. Belt maintenance should include regular checks of belt condition, belt alignment, and tension. You should also perform frequent inspections of the sheaves and shafts. You may need to replace belts that are worn or damaged from overheating or contact with oil or grease. Never replace just one belt of a multi-belt drive. Replace them all. Belts stretch with use. If you replace one belt, it will tighten all the others. Automotive belts start with either 4L, which is 12.5 millimeters wide, or 3L, which is 9.5 millimeters. The numbering following it is the outside length of the belt in tenths of inches. That's about 2.5 millimeters. The inside length of the belt is typically 2 inches, 50 millimeters, less for a 4L belt, and 1.5 inches, 38 millimeters, less for a 3L belt. An example would be the 4L 460, which would be 46 inches, 1168 millimeters long, outside, and 44 inches, 1118 millimeters, on the inside. In contrast, classic V-belt numbers start with a letter identifying the cross-section, A through E. A series belts are the most common. The number following is the inside length in inches. The outside length is typically 2 inches, 50 millimeters, more. An example would be A44. This is 44 inches long on the inside, 46 inches on the outside. In other words, it's equivalent to the 4L 460. Classic cog V-belts deliver more horsepower and last longer than conventional belts. They have fully notched cogs for maximum flexibility. There's a high coefficient rubber edge. It's oil resistant and static conducting. They're a proven energy saving design that outlasts conventional belts. Fewer belts are required and drive weight is reduced. DV wedge belts are oil resistant and static conducting. They permit compact, lighter weight drives. High strength tension members deliver maximum power with minimum stretch. They're built for long-term dimensional stability. Molded cog construction under 5 meters, 5,000 millimeters in belt length. The classic V-belt, A, B, C, D or E, has a cable called envelope construction. It runs cool and is flexible and has strong tensile cords which minimize stretch. It is static conducting and heat and oil resistant. It's tolerant to shock loads. Noise can be caused by the slapping of belts against drive guard or other obstructions. Squealing of belts while running is usually caused by poor tensional drive or by build-up of foreign material in sheave grooves. It can also be caused by oil or grease between belt and sheave groove. It's important to look at the tight side of a drive to be sure all the belts are running tight. If one or more belts are running loose, the drive needs to be retensioned. This could be caused by uneven wear of the grooves in the sheave. Maintaining correct tension is the most important rule for V-belt care. Belts too loose will slip, causing excessive belt and sheave wear. Belts that sag too much are snapped tight suddenly when the motor starts and when peak loads occur. This can actually break a belt. Worn or damaged sheaves can cause sidewall wear, or the belt rubbing on the guard, or misalignment, insufficient tension, wrong belt type, improper storage, excessive heat, excessive oil or grease, an abrasive environment, excessive moisture, or improper tension. All of these can cause sidewall wear. Cover or soft par or swollen can be caused by the belt being improperly put on or improperly prized. Defective or worn backside wear can be caused by wear in the backside idler or excessive exposure to oil or grease. Spin burn can be caused by worn or damaged sheaves, insufficient tension, incorrect belt cross-section, excessive oil or grease or moisture, or overdriving the belt. The belt may also have been damaged when being pried on or off. Cracks in the underside of the V-belt are caused by excessive heat, incorrectly sized sheaves, specifically they're too small, or incorrect or prolonged storage. It can also be caused by excessive water or grease. If the V-belt cover is split or the cogs are missing, this is normally a sign of mechanical damage caused by incorrectly installing the belt or removing it by prying it, or some foreign object. All sheave grooves should be smooth and uniform. There should be no burrs and rough spots. Dust, oil and foreign matter must not be present. If the sheave walls are permitted to dish out at the bottom, the belts will be ruined. They'll quickly have their bottoms chewed off, and the belt wedging action is reduced, and so it loses grip and will slip. Shiny groove bottom indicates that either the belt or sheaves are badly worn, and the belt is bottoming in the groove. Badly worn grooves cause belts to ride lower than the rest of the belts. An effect is similar to mismatched belts. Belts riding high in the groove travel faster than belts riding low. You can check the sheave dimension using a sheave gauge. Belts that are too worn will slip. This will cause excessive belt and sheave wear. Make sure drive shafts are parallel. Where shafts are not parallel, belts on one side are drawn tighter and pull more than the share of the load. If misalignment is in the sheave, belts will enter and leave the grooves at an angle, causing excessive wear. The shafts must be parallel or the life of the belt will be shortened. The first step is to level the shafts. This is done by placing a level on each of the shafts. Then shim the lower side until the shaft is level. Next, make sure the shafts are parallel. This is done at different points on the shaft. And adjust the shaft until they are equal. Distance apart, make sure that the shafts are pulled in as close as possible before performing this procedure. Basically, any degree of misalignment, angular or parallel, will decrease the normal service life of a belt. Angular misalignment results in accelerated belt sheave wear and potential belt stability problems with individual V-belts. A related problem, uneven belt or cord loading, results in unequal load sharing within multiple belt drives and can lead to premature failure. Symptoms such as high belt tracking forces, uneven tooth-lined wear, edge wear, high noise, and tensile failure are indicators of misalignment. Wide synchronous belts are more sensitive to angular misalignments than narrow belts. Parallel misalignments also result in accelerated belt and sheave wear and potential belt instability. Uneven belt and cord loading is not as significant a concern as with angular misalignment. However, parallel misalignment is typically more of a concern for V-belts. Parallel misalignment is generally not a critical concern with synchronous belt drives as long as the belt is not trapped or pinched between opposite flanges and as long as the belt tracks completely on both sprockets. Shaft alignment can be checked by measuring the distance between the shafts at 3 or more locations. If the distances are equal, the shafts will be parallel. To check the location of the sheaves on the shafts, a piece of string can be used. If properly lined up, the string will touch them at the points as indicated. Rotating each sheave a half revolution will determine if the sheet is wobbly or the drive shaft is bent. The most important factor in the operation of V-belt drives is proper belt tensioning. Belt tension must be sufficient to overcome slipping under maximum load. To increase total tension, merely increase the center distance before attempting to tension any drive. It is important that the sheaves be properly installed and aligned. If a V-belt slips, it is too loose. Add to the tension by increasing the center distance. Never apply belt dressing. When you replace a belt, always check the tension immediately after installation. Then check the tension again after 24 hours of operation. You can check the belt tension using a belt tension gauge. Always check the manufacturer's information to set belt tension. A continuously variable transmission, CVT, also known as a single-speed transmission, stepless transmission, pulley transmission, or in the case of motorcycles, a twist and go, is an automatic transmission that can change seamlessly through a continuous range of effective gear ratios. This contrasts with other mechanical transmissions that offer a fixed number of gear ratios. The flexibility of a CVT allows the input shaft to maintain a constant angular velocity. A belt-driven design offers approximately 88% efficiency, which, while lower than that of a mechanical manual transmission, can be offset by lower production costs and by enabling the engine to run at its most efficient speed for a range of output speeds. When power is more important than economy, the ratio of the CVT can be changed to allow the engine to turn at the RPM at which it produces greatest torque. This is typically higher than the RPM that achieves peak efficiency. In low mass, low torque applications, such as motor scooters, a belt-driven CVT also offers ease of use and mechanical simplicity. Belt preventive maintenance. Check the belt tension using a belt tension gauge. Measure the deflection and tension of the sides of the belts. Be sure to write tension and deflection specifications for the mechanic on the preventive maintenance checklist. Identify any type of oil, grease, or chemical within a meter of the belt. Check sheave alignment. If sheaves are not aligned to manufacturer specifications, then slippage can occur. Check the sheaves for wear using a sheave gauge to ensure the sheave is not worn. That's the end of part 3.